This video is going to look at solving exponential equations with common bases. That means the number that has the exponent is the same. So if we were looking at 2 to the x, and we knew that that equaled 2 to the 5, this is a problem where we have common bases. The base is 2. Now let's think about what this says. 2 to some unknown number is 2 to the number 5. So, think it through again. 2 to some unknown number is the same as 2 to 5. So that number, that missing number, is 5. We can say that x equals 5. This is where solving with common bases is kind of nice, because if you have b to the x equals b to the y, they have common bases, then you know that x equals y. Always, this is always true if you have common bases. Sometimes you don't have common bases and we need to solve using another method, which will be in another video. But more often than not, you can make common bases using what you know about exponents. So here we have 6 to the negative 2a, and we know that it equals 6 to the 2 minus 3a. So to figure out if we can solve this using common bases, we have to look at the bases. 6 and 6, they're the same. So what we know is that the two exponents are equal to each other. So we know that negative 2a equals 2 minus 3a. Now we have a basic equation that we can solve using stuff that we've been doing for ages. Add 3a to both sides. So you get a equals 2. Now that you've solved this equation, you can always go back and plug it back in to see if you get the same thing. Let's go ahead and plug back in for this one just to be good math students. 6 to the negative 2 times 2 hopefully will equal 6 to the 2 minus 3 times 2. Well, negative 2 times 2 is negative 4. 2 minus 6 is negative 4. Yay! We have the correct answer. So in this case, we had common bases that were easy to see. We set the exponents equal to each other, and we're good. Alright, so here we have 3 to the x plus 5, and we know that it equals 81. Uh-oh, they don't have common bases. Obviously, I have a base of 3, but I have 81 to the 1. That doesn't help me over here. So before you give up and try to say, oh, it's not possible, think about the number 81. Is there any way you can write 81 with a base of 3? Well, 81 is 3 to the 4th. So we can rewrite our equation as 3 to the x plus 5 equals 3 to the 4th. Now we have common bases, and we can set our exponents equal to each other. So we can say that x plus 5 equals 4. This is the easy one to solve. We get x equals negative 1. Again, you can plug it back in to check your solution to see if you got it right. So 3 to the negative 1 plus 5 should equal 81, or 3 to the 4. Negative 1 plus 5 is 4, so we did it right. With our exponential problems, we also have that natural base e. But we can still solve using common bases again, because both of these expressions on both sides of the equation have a base of e. So we can just go ahead and set our exponents equal to each other. E to the negative 3 equals e to the 4x plus 1. So we can say that negative 3 equals 4x plus 1. And now it's just a matter of solving. So we'll get negative 4 equals 4x. Divide both sides, and we get x equals negative 1. Eek! Here's another one where we don't have an obvious common base. I have a base of 4, and then I have a base of 8. These are not exactly the same. So we want to think about a way. Can we write 8 as 4 to the something? Can we write 4 as 8 to the something? No. But 4 is the same as saying 2 squared, right? So we could say 2 squared to the 5 minus 9x equals 1 over 2 cubed to the x minus 2. So this kind of helps me out a little bit. I have a common basis. However, one of those bases is in the denominator. So now we have to think back to our rules of exponents. That 1 over 2 cubed is really, could be rewritten as 2 to the negative 3. Having that negative exponent is what moved it to the denominator in the first place. So we could be looking at 2 to the negative 3 to the x minus 2 equals 2 to the 2 to the 5 minus 9x. Now I have common bases and I can go ahead and set my exponents equal to each other. I'm going to be really careful about this though, because this is 2 times that. We remember our laws of exponents. 2 times 5 minus 9x, I need to use parentheses. On the other side, we have negative 3 times x minus 2. So again, we need to use parentheses. We have to be really careful. We're going back to distribution. These are things we learned ages and ages ago, but that will carry true throughout all your mathematics experiences. Distribute. So we're going to end up with 10 minus 18x equals negative 3x plus 6, because I did not fall for that. Now I'm going to move all my x's to one side and all my numbers to the other side. So I'm going to add 3x to both sides. And so we're going to end up with 10 minus 15x equals 6. Now we're going to subtract 10 from both sides. So get negative 15x equals negative 4. Divide both sides by negative 15. So we end up with x equals 4/15, which is perfectly fine. We can have fractions as our answers. If we were to go back and plug them in, we would see that this made the equation, the original equation, true. A little bit tricky on this one because we had to make common bases by doing a little bit of work. But once we had those common bases, we were able to set up just a basic equation. Alright, this is the last equation we're going to look at. Let's figure out what our bases are first. We have a base of 16, we have a base of 4, and we have a base of 2. So it looks like our least common base in this case is going to be 2. I'm going to work with 2. I know that 16 and 4 have some other possibilities, but since the smallest base is 2, that's the one we want to work with in order to make the common base. So let's start with the 16. How can we write 16 as 2 to some power? 16 is 2 to the 4th. So we can say that this is really 2 to the 4th to the 2p minus 3 times 4. How do we write 4 as the power of 2? It's 2 squared. 2 to the 2 to the negative 2p equals 2 to the 4. Now before we start setting things equal to each other, we need to look at this left-hand side. We need to think about our rules of exponents. We can, when we multiply things that have common bases, what do we do with the exponents? We add the exponents. So I'm going to simplify this a little bit further so we can kind of see what's going on. This is 2 to the 4 times 2p minus 3 times 2 to the, I'm just going to say negative 4p, equals 2 to the 4th. Since these two guys have a common base, and I'm multiplying them, I can add the two pairs of exponents together. This is why we have to think about our laws of exponents before we even start solving these kind of things. We know that 4 times 2p minus 3 plus negative 4p, that becomes our left-hand side. We can add those two exponents together and just use one base of 2. Now, finally, we can solve. There's one exponent, there's the other exponent. So we have a big giant equation, but all we're doing is using our basic algebra. So we have to start out distributing. So we're going to end up with 8p minus 12 minus 4p equals 4. I'm going to move on up for a little bit. Combine like terms, we'll get 4p minus 12 equals 4. Add 12 to both sides, so we end up with 4p equals 16, and p equals 4. Again, we had to do a little bit of legwork in order to make common bases, but once you see how to solve when we don't have common bases, you're going to be looking for them all the time. Solving using common bases is a very handy way to solve exponential equations.